How's it going, everybody? We got a motorist is traveling along a straight portion of a highway. All right, is decreasing the speed of his automobile. Well, decreasing the speed. That's important. That's going to be what, an acceleration at a constant rate. Yes, constant acceleration. So I got some equations there. Before exiting from the highway onto a circular exit ramp with a radius of 560 feet. So he goes onto a circular exit ramp with that radius. And so you could say for this, we're going to have A equals constant. All right, and then for this, we're going to have normal tangential coordinates. All right, and so he continues to decelerate at the same constant rate. All right, and so we know that during this normal tangential, we still have A equals constant. All right, it takes 10 seconds. After entering the ramp, his speed has decreased to 20 miles per hour. All right, so I guess to kind of see if we can get like a visual of this. In the beginning, he's traveling on some straight portion. All right, he's moving, and he has an acceleration. So some acceleration value, we'll call it A1. All right, so it'll be negative, but that's not important right now. So he's some acceleration value. All right, he's gonna hit this space where he's gonna start moving in a circle. Okay, and so we're gonna say, they say it takes 10 seconds. So they say in this space, we'll just say this space right here is going to be a 10-second space. I don't know how long it is. I just know it's 10 seconds long for him to kind of get to that far. They say that his acceleration is going to be the same value as before. And so we know for this 10-second space, we can say he has some acceleration. We'll call it acceleration 2. And we know that it's the same as acceleration 1. All right. Excuse me. We know it's the same as acceleration 1. However, because it's only talking about changing the velocity, we know that it has to be a tangential acceleration. So the tangential acceleration of this space is going to be the same as the space where he was moving straight. All right, cool. So we know that. We say a speed he's going to maintain. So I guess after the 10 seconds, he maintains his speed. And so from this space, let's just say that's after the 10 seconds and onward, he's going to maintain his speed. So velocity is constant, which means acceleration equals 0. Tangential acceleration specifically equals 0 for this space. So we'll call it A3 and we'll say it's tangential and it'll equal 0. So we'll say that's our third domain. All right. So we got 3 spaces we're working with: space 1, space 2, and then space 3. And so we know the acceleration is associated with those. All right. So we got A3, A2, A1, where A2 and A3 are going to be circular motion. And so we're going to use tangential acceleration, not maximum acceleration, or full acceleration, excuse me. All right, cool. So let's see what else we got. Knowing that it is constant speed, the total acceleration of the automobile is equal to 1/4 of its value prior to entering the ramp. So at the constant speed, he says, at the constant speed, at this point I've highlighted the whole problem, but at this constant speed, so we're talking about space 3, he says in space 3, the total acceleration, which we know A3 is going to be the square root of AN squared, 3 squared, plus AT squared. We say what is 1/4 the value of the acceleration prior to entering. So prior to entering, we're talking about A1. So it's going to be equal to 1/4 A1, not equals 1/4 A1, which is the same thing as 1/4 A2 T. So we could put 1/4 A1 or we could put 1/4 A2T to get the same value. All right, cool. Determine the maximum value of the total acceleration of the automobile. All right, so the maximum value is going to be the one where it's biggest. So in state 1, 2, 3, one of those is going to have the big value. All right, so let's kind of pick it apart. State 1, he's only moving straight, so he's going to have some acceleration. Cool. State 2, he has a circular acceleration. And we know with the circular acceleration, it's going to follow the n squared plus t squared. And so what happens is we know for state 2, I guess I'll put, I think I'll start doing it in colors actually. I'll do it like this. I'll say state 1, it has some value. I don't know it yet. State 2, I think I'll put in purple. State 2, we know he has a normal acceleration squared and a tangential acceleration squared. I don't know why I always put the normal acceleration first. I don't know why I always do that. I guess because we say normal tangential, I always put normal first. And then for state 3, we know we have the same thing, AN3 and that's squared, and then AT3 squared. One of these is going to be the biggest one. So let's pick it apart. They want to figure out which one of these is the biggest, and whenever we figure that out, we're going to get the answer. So let me erase some of this stuff because at this point I've just highlighted the whole problem. All right, let me put this part maximum value. Total acceleration. All right, so one of those is going to be it. We have to figure out which one is going to be which. So we got some information. We got to pick it apart. Oh, I didn't talk about this 20 miles per hour. So the 20 miles per hour pertains to this guy. And so what I'll do is I'll just kind of label it under state 3. So I'll say for state 3, we know the velocity is 20, I'll put V3, that's 20 miles per hour. But I want to convert that to meters per second. So let's see. Hours got to convert. So 1 hour is 3,600 seconds. The hours cancel. Miles got to go to the bottom. It's 5,280 feet in a mile. So when I convert that, let's see, when I convert that, we have 29.33. And that's going to be feet per second. So we know in the space where he's traveling, he's still on the curve now. I didn't really draw it well, but he's still on that curve. All right. But we know he has this constant velocity at that part. So we know his velocity is 29.33. With the constant velocity, I can find his normal acceleration. Cool. He also tells us that we also know because the velocity is constant, the acceleration, the tangential acceleration has to be 0. Okay. And so we actually know everything we need to know about this part. So I can say the tangential acceleration is going to be 0, which means this. A3 is just going to be made of AN, which is just going to be V3 squared over R, which is going to be 29, why does it keep doing that? 29.33. And that's squared divided by, I think they said it was 560. Let me check that really quick. Yep, 560. All right, great. So at the end of the day, A3 is going to be A3 is going to be 1.537, and then that'll be feet per second. All right, cool. So now I have some more information. So I think I'll just put what I know in. I'll just underline it for now. Double underline. Bam. So now I know that. I also know my V2. Or my V3, excuse me. All right, so I'm picking the problem part. Let's see what else. So I know the acceleration at 3. I don't know 2 and 1, so I got to compare them. I got to figure out 2 and 1. Fortunately, they did tell us something else that we needed to know, and I wrote it down already. We know A3 is going to be equal to 1/4 of A1, which is also going to be 1/4 of A2. So I'm going to use that to get an answer. So A1 is equal, if you rearrange the algebra, A1 is going to be 4 times A3. All right. I know A3 is 1.57, so A1 has to be, let's see, times 4, 6.146. And that's going to be feet per second squared. So I know A1. Mind you, because A1, he's not moving in a circle, that's just going to be it for him. And now that being said, I can go to A2 like this. A1 and A2, AT2 are the same. They told us that. All right. And it comes from, let's see. They say he continues to decelerate at the same constant rate. So basically from the space where he's moving on this straight part into the time where he moves on the curved part for the 10 seconds, it's the same deceleration. Deceleration always corresponds to tangential acceleration on a circle. So we know AT2. All right, cool. So we got that. But we don't know AN2. So conceptually speaking, A2 is going to be the biggest one. How do I know that? Because of this. He's going to come in with some velocity here. We don't know. We're going to call it V1. That's the velocity he has at the end of V1, right? So at the end of this time, he's going to have a velocity right there. So we're going to call that guy V1. So he's going to hit the 2 segment with V1. And then by the time he finishes the 2 segment, he's going to go this distance. And what's going to happen is he's going to get here. And at this point, he's going to have this velocity, the 29.33. So he goes from V1 to V2. So that's important, V1 to V2, but he's decelerating. So what that means is V1 is going to be bigger than V2. So when I'm trying to calculate my normal acceleration, I want to calculate it so that I get the biggest normal acceleration possible, because I want this whole value to be the biggest value possible. The tangential is going to be the same because it's constant. So that's got no bearing on me. My bearing is to look at the normal. So I have 2 options. I can plug in this 23 into my normal and I'm going to get an answer. All right. But that's going to represent his acceleration at that space right there, right at the edge. But that's not what I want. If I try to find it right at the beginning of his motion, right here, all right, that's going to be his fastest point when he's hitting the curve. And so what we're going to need to do is find this guy. Well, they told us the time. So they said the time was 10 seconds. They told us the velocity 29.33. We know he's going to go from, I don't know why I put 1 to 2 there. I should have said 1 to 3. So not 1 to 2, but 1 to 3. Okay. So I know V3, which would be something like a V final. They don't tell us to change of position. V final equals V initial plus acceleration times time. I got time, I got acceleration, I got the final velocity. Yes, this is the one I'm going to use. All right, cool. So with that being said, I can do this. I know that the V final is going to be V3. A lot of people are going to kind of mess that up. I can feel that. A lot of people are going to mess this part up. They're going to put it here, and that's not the right spot. Remember, it starts at V1, then it goes to V3. So that's what we're going to have as our final. Okay, so what we're really looking for is our initial velocity. So writing that out, VI is going to be 29.33 minus the acceleration, because I'm moving this term over. So minus the acceleration. The acceleration was 6.146. That's his tangential. All right. But mind you, he's decelerating. So when I subtract it, it's going to be a deceleration. So 6.146. And then the time is 10 seconds. And so what ends up happening is these 2 values become a positive, and I just have to add it all up. So let's see. So VI is 90.79, and that'll be feet per second. And that makes some sense. So this velocity is going to go here, okay, for our AN squared. So now we can bring everything together and we can say A2, which I know is going to be the biggest now, is going to be the normal squared. The normal is 90.79 squared divided by 560. I got to square that. All right, actually, you know what? Instead of no, I'll just square each term. So squared becomes a fourth, and then this becomes squared. Yep. Plus the tangential, and we know the tangential is this because it's constantly it's that way the whole time. So 6.146 squared. All right, so I got my tangential squared, take my square root, and then that'll give me my answer, 15.951, and that'll be its acceleration, so feet per second squared. So that is my answer. And this problem was kind of involved. You have to really be able to pick it apart. So just kind of reading the problem statement made all the difference, and being able to really pull out all that information. All right. But you read it as many times as you need, and each statement, just like how I went through, I highlighted and I kind of correlated that to an idea. Pulling that apart, we were able to pull our problem into 3 sections: state 1, state 2, state 3. We get this final piece of information where they told us this right here, which was the key to relate state 3 to state 1 and state 1 to state 2. So basically we were able to relate A3 to A2, and then from there we were able to realize, keeping A3 and A2 in mind, we were able to pull out everything we needed for A2. All right, but you had to go find your velocity, because you had to realize this: his velocity is going to change in the whole part. So at A2 he's going to start at V1, then he's going to go to V3, all in the space of A2. And so you have to kind of be able to figure that out, that that's constant acceleration. Use your constant acceleration to backtrack to get V1, because V1 was bigger than V3, and we want the biggest value possible. Plugging all that in, we get their answer. So engineering should not be as hard as they make it out to be when you're in college, and I'm just trying to do what I can to make things easier. So I hope this helped.